Welcome to the lecture series on Digital Electronics and Computer Organization. I am Dr. Michael, Associate Professor CSE Department, MLR IT. Today we are going to discuss about comparators. So what all we are going to discuss in today's class is, first of all, why we need to study comparators, and then we will study what are comparators. We will start with 1-bit comparators, and then we will extend the idea of 1-bit comparator to n-bit comparators. So today's class we are going to discuss all these topics. So first of all, why we need to study comparators? Because digital comparators, they are the fundamental blocks in digital electronics, right? And not only they are useful for comparison, after comparison, for example, we do sorting, so the comparators are also useful for sorting. They facilitate sorting and also filtering. Also, now based on the value compared, there could be some control operations that we do, and those control signals can be generated, right? And when we compare, there is also scope for correcting errors. As a result, comparators are useful in various practical applications. Not only these, but they are also useful for troubleshooting digital circuits. Okay, so first of all, as discussed, let us start with a 1-bit comparator, and then we will extend that idea to n-bit comparators. Okay, so first let us keep it very simple. 1-bit comparator means we compare two variables, each is of size 1 bit. So A is of size 1 bit, B is of size 1 bit. We know very well that when there are two variables, each of 1 bit size, the total number of combinations is 4, which are 0, 0, 0, 1, 1, 0, 1, 1. So these are the 4 possible combinations. Now, the truth table of a simple comparator can be constructed in this manner. So let us say here the output is 1 when both A and B are equal, otherwise it is 0. Here, first case, A is 0, B is 0. So both A and B are equal. So we get a 1 here. Second case, A is 0, B is 1. They are not equal, right? A is 0, B is 1. 0 is not equal to 1. That is the reason here we put a 0. Third case also, A is 1, B is 0. They are not equal. So we give a 0. Again, in the last case, similar to the first case, both A and B are same. A is 1, B is also 1, hence the output in this case is 1. So we have seen a simple comparator. Now, in general, any comparator will have these 3 categories. Either A is equal to B, or A is less than B, or A is greater than B. The same thing is valid for any comparator. Let it be 1-bit comparator, 2-bit comparator, right? So in general, whatever logic that we discussed is valid for n-bit comparator also. So here, now what we will do is standard process. We got the table, truth table from the logic, right, which we just discussed. Now based on this truth table, we will identify what is the circuit or the logic gate which will perform such an operation. Now if we look at this truth table carefully, A and B are inputs. A equal to B, which is represented by F naught, this is the output, okay, A equal to B, which is represented by F naught. This is the output. Fine. So now which is the logic gate which satisfies this truth table? It is XNOR gate. Hence what we can conclude is an XNOR gate will act as a comparator where it will tell us whether A is equal to B or not. Now, as discussed in the previous slide, other than A equal to B, we have other categories: A less than B, A greater than B. Let us slowly extend this logic for those cases also. So here again we are taking two inputs. Possible combinations are 4, 0, 0, 0, 1, 1, 0, 1, 1. Fine. In the previous slide, we have already seen this case where A equal to B, in this case X equal to Y. Now, let us discuss this particular case. What about X greater than Y? So, again this truth table we can easily construct. How? Wherever X is greater than Y, okay, the output is 1. Otherwise, the output is 0. So, here they are equal. So, X is not greater than Y. Hence, we are putting a 0 there. Next, here X is less than Y. X is 0, Y is 1, 0 is less than 1. So, condition fails. Hence, we indicate it by a 0. Now, what about this case? X is 1, Y is 0. We know very well that 1 is greater than 0. Hence, this particular relation is true, which we represent by 1. Last case, again X is equal to Y. X is not greater than Y. Not greater than Y. So, we put a 0 there. Okay, right? So, here only one case where X is greater than Y. Hence, okay, in all the possible outputs, there is only one case we get a 1. Now, let us use the same analogy which we have just considered for the last case. What about when X is less than Y? Again, here first case X is equal to Y. So, false, we represent it by a 0. Next, here X is 0, Y is 1, so X is less than Y, hence we put a 1 here. Okay, right? Again, this case, in fact X is greater than Y, so we give a 0 there. It is false. X is less than Y is not satisfied. It is false, so we put a 0 there. Next, what about the case of 1, 1? They are equal. So, again this case is violated. So, we put a 0 there. So, at only one particular case, right, we have the X is less than Y. Fine. So, only in the output column, only one place we have ones, rest all we have zeros. Now, what we will do is, based on this, let us construct the circuit. So, in the previous slide, we have identified that this particular relation we get for an XNOR gate. So, X XNOR Y should give us X equal to Y. So, here we have X and then here we have Y. So, both going as inputs to an XNOR gate is giving us X equal to Y. That part of the circuit already we discussed. Now, what about this one and this one? So, first let us analyze the first output column, for which we have to closely look at this. Here in this case, there is only one situation where the output is 1. So, easily we can get the Boolean expression for this. How? Here xi is in its true form. So, simply take xi and here yi is in its, yi in this case is in its complementary form. So let us take yi bar. So the simple expression for this particular x greater than y is xi into yi bar. Now how can you develop circuit for that? Let us see where xi is. Okay, so this is xi. Then we need yi bar. Yi, when we connect to a NOT gate, we are going to get yi bar. So in this manner we got the yi bar. In this manner we have got the yi bar. Okay, fine. So here we are going to get yi bar. So xi into yi, multiplication is done by AND gate. Okay, so output of AND gate will give this, and that is what we were trying to do. Fine. Now the last column only is pending. If we complete that, we complete the circuit diagram. So how can we get this? Again we will see inputs and only the last column, because we have to develop the circuit for the last case, which is x less than y. Now how can we do that? Again there is only one case where the output is 1. So this case, right? So based on the previous logic, here the output will be xi is 0, so xi bar, yi is 1, so we will take yi, xi bar into yi for x less than y. So here xi bar means xi we have to pass it via NOT gate. NOT gate will complement, so we are going to get here xi bar, and that multiplied by yi. Okay, we have discussed that multiplication will be performed by AND gate. So we put all these into an AND gate, then we are going to get x less than y. So this is the complete circuit diagram, which will work as a 1-bit comparator. So what we can do here, we can use toggle switches to either give zeros or ones at the input, and based on whether they are equal or less than or greater than, the outputs here can be indicated on LEDs. Now this idea of 1-bit comparator we can easily extend to n-bit comparator. Let us start with a 2-bit comparator. 2 bits means A, the input A is of 2 bits, the input B is of 2 bits, right? So total there are 4 inputs, fine. So the total number of combinations will be 2 power 4, which is 16. So 1, 2, 3, 4, 5, 6, so on, okay, 7, 8, 9, 10, so on, we have 16, okay, 16 combinations of input, all of you can count that, okay, right. Now what we need to do here is how to compare whether A is equal to B or not, okay. So here what we need to do, if they are equal, we are going to put 1, this is 0, 0, this is 0, 0, so on. Rest all cases, okay, rest all cases it is not satisfied. Again in this case, 0, 1, 0, 1. A is also 0, 1, B is also 0, 1, means A is equal to B, so we put a 1 here. When the condition fails, we put a 0, when the condition is satisfied, we put a 1. For example, let us take this case. A is 0, 1, B is 1, 0, they are not equal, so we are putting a 0. Last case, let us check. A is 1, 1, B is also 1, 1, both are equal, so true case we will put a 1. So in this manner we can construct the truth table. In the previous case we have seen that from the truth table we can easily construct the circuit diagram which will give such a functionality, right, fine. So just based on logic, if they are equal we can construct a truth table. Now from the truth table easily we can develop the circuit diagram for the n-bit comparator. Okay, right? So I will leave this for your exercise. You don't need to by heart, just take pen, paper, right? You get expression. Of course, when the expression is complicated, you will have to use K-maps to simplify the expression, right? So this is the basic idea how you can develop circuits which will perform comparison. So in today's class we have seen why we need comparators, we have seen 1-bit comparators, we have extended that idea to n-bit comparators. That's all for today's class. Thank you very much.